Hi everyone and welcome to this new video. Today we are here to talk about quantum field theory. This is the second lesson about this topic, and today we are going to talk about Lie theory, so Lie groups, Lie algebras, representation theory, and a bit about Dinkin diagrams. Okay, perfect. In the last lesson we talked about quantum mechanics. And we talked about brackets notation, so Jerkin notation. We talked about canonical quantization, but we didn't see creation and annihilation operators. And to see this operator formulation, we have to wait I think the five lesson about quantum field theory. So QFT. Today we are going to talk about Lie groups. Perfect. To understand this video, you must know about something about differential geometry. So, for example, what's differential manifold? So, what's a smooth manifold? You have to know what is this. Okay, perfect. Perfect. So, let's start with the definition of Lie group. So, the formalism of Lie groups, of Lie theory and physics is very important because we can use it in many branches of physics. For example, quantum mechanics, quantum field theory, and so on. Quantum mechanics, classical mechanics, and so on. In the next video, so in the next lesson, we'll talk about symplectic geometry, and so we are going to talk about what's a symplectic manifold, what's an Hamiltonian formulation, Poisson brackets, and so what's the symplectic geometry? Symplectic geometry is a symplectic version of differential geometry. So we begin to a definition of differential smooth and topped by symplectic form, and so then we can introduce Poisson brackets and so on. Whereas in this lesson we are going to introduce, for example, Lie brackets, not Poisson brackets, Lie brackets, and so Lie derivative, Lie brackets, Lie groups, and Lie algebras, and Lie algebra. Yeah. Okay, perfect. So, what is a Lie group? So, a Lie group is a particular type of group. Okay, it's a particular type of group, and so we have definition. Okay, perfect. Okay, a Lie group. A Lie group, so G and topped by group operation points. Okay, to talk about, for example, group operation, I use the notation of a point. Okay, so this point is a group operation. So operation that make this set of numbers, for example, a group. Okay, so I have a Lie group G point is what is one. First point is a group. So a Lie group is a group. Okay, so it's a group G with group operation, of course. Where are you from? Italy. I think Italy. Yeah, I speak English, but I'm from Italy, and so a group is a group. Perfect. Is a group G. Then G is a smooth manifold. So as a smooth manifold. And then we have this map, this particle map, G, G1, G2, high, G. So, a Lie group has a smooth manifold, okay, as a smooth manifold. For example, this is a manifold, a smooth manifold, a differential smooth manifold. And so, when a manifold is smooth, when, of course, I have the transition functions are smooth. Okay, and I have that then. So it's a smooth manifold with a structure with a group structure. Okay, and so this manifold is a group 2, and then I have these two maps, 1 and 2. The first map takes two numbers of the group and give the multiplication, for example, between these two elements. So these two elements combined by a group operation. And then I have the map I, and this map takes an element of the group and gives the inverse element of the group. Perfect. Okay, now examples. So I maybe in the chat there is someone that knows what's some example. For example, some example. Sorry. So someone in the chat knows what is some examples. So an example of a Lie group. And for example, G is equal to R to M. This is an example. This is an example of a Lie group, and group operation point is equal to the sum. Okay, sum defined over R to M. Okay, so this is a Lie group, and attention please, because sorry. Because R to N is the translation group. Translation group. Here we are. So this type of group, R to N, and the group operation is the sum of defined over R to N, is the translation group. It's called the translation group. And this is an important example, for example, in quantum mechanics too. Okay. Another example. Do you know something about this topic? If you wanna say something. Okay, physics and math. So, for example, this lesson are inspired by a lectures video of the Professor Frederick Schuller. So, if you search Frederick Schuller on YouTube, you find him, and he's a professor at the University of Nuremberg, I think. And so this professor did these lectures about differential geometry and Lie theory. And then for another PDF, I think many books about quantum field theory talk about Lie theory too. So I think a great book about quantum field theory talks about Lie theory too. Oh, living in London is fantastic. It's a great place. I think the best way to learn English is watching series. So TV series from I learned to speak English watching, for example, Marvel films. Okay. Now, and studying over books written in English. Perfect. Now, so Friedrich Schuller is a great professor. So watch this lecture. Watch his lectures. Perfect. Okay. Now, another example. Another example. Okay. Example maybe here. Oh no. That's dirty now. So another example is S1. So the circle, okay? The circle, and this is defined as the set of every complex point, okay? Of every complex point, such that this is equal to 1. So what does it mean? I have the complex plane, and so here I have a number, a complex number, and the length of this complex number is equal to 1. Okay, is equal to 1. Now, this is a Lie group. This set is a Lie group. So which is the group operation? The dot. Okay, I have the multiplication over C. Okay, so I have the multiplication over C, and so multiplication between two numbers, two complex numbers. Okay. Perfect. Now, so S1 multiplication over C as a group is the Lie group, and this group is defined as the U1 group, and this is an important group in the world of quantum mechanics. In fact, I have that this group is used in quantum mechanics to transform two vectors. Okay, so for example, I take the vector psi, and then I have the vector u psi, u for psi, and this is psi prime. Perfect. So it's a transformation between two vectors in quantum mechanics, and I have that this is an operator, an unitary operator. Okay, perfect. So this is the Lie group. This is the Lie group, and now another example. Another example. Oh yeah, this is an important group because it's so useful in physics that I don't know a particular branch where it's so useful, because it's useful in every branch of physics. Okay, perfect. Now, so this group is called the general linear group. General linear group. And so I have G is equal to the set of phi of every function phi of this kind, such that the determinant of phi isn't equal to 0. Isn't equal to 0. And this is defined as the general linear group NR in this case. Okay, so this group is very important because it's used in many parts of physics, in many branches of physics. Okay. Henry. Okay. Hi, Henry. Hi. Perfect. So this is the Lie group of the set of every function of this kind. Okay, so this is the general linear group. Okay, Mac. What does it mean? Why reciti? Perché proprio reciti? Quindi, stavo parlando, devo tornare nella mod inglese. So this is the set of every function of this kind. So in fact, before I said a set of numbers. So a set of numbers G. There are some cases where the G isn't a set of numbers. For example, this case. This case is a group, so as a set is a Lie group, and is a set of functions, not numbers. Okay. Perfect. So now another example. Oh, sorry, the group operation here. The group operation as the composition between maps. Okay, so for example, I have phi and psi. Okay, so the composition map. I have two. I have Rn or subset, and then I have psi, and then I have phi over Rn. Okay, perfect. Now, now we can talk. So this is the introduction to Lie theory. So now we've seen what's a Lie group. What's a Lie group? So repeat, a Lie group is a Lie group with a group operation as a group G, and we know what's a group. Yeah, right. We know what's a group, right? I think, yeah. Yeah, we do. Okay. If you don't know what's a group, you can watch my video about this. Okay, about this topic, what's a group? It's the first video in the course of mathematical methods for quantum mechanics. It's the first video. Okay, about yes. So green knows what's a group. Perfect. So it's a group. A Lie group is a group and is a smooth manifold. Okay, and then I have these two kinds of maps, mu and I, and the first map takes two elements of the group and gives the operation between these two elements. The second map takes just an element of the group and gives the inverse of this element. Perfect. And the property of these two maps is that both are smooth. Okay. Perfect. A questo punto dico un attimo anch'io in italiano, dove puoi allora, i PDF, guarda, non sono brava. PDF di studiare all'inizio non so. Se riesci a trovare il PDF di un libro come per esempio Che cos'è la matematica? Che cos'è la matematica? Che è un libro fatto molto bene, che parte dalle basi, e poi invece di fisica, un libro Fisica per non fisici, che sono tutti e due libri un po' divulgativi, ma che ti gettano le basi, euristicamente, per un po' tutta la fisica e tutta la matematica. Okay, we can turn in English mode. Now, to define the Lie algebra, we need some other elements. Okay, so now definition, another definition. Oh. Okay. 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 Now, we can talk about left translation. Okay. So we can take a Lie group G with an operation point. Okay, and this is a Lie group. Lie group. So sorry, I forgot this definition. So let G be a Lie group, G with an operation, and for every point, for every element of this group, there's a map. There's a map LG to G, from G, sorry, to G, a map from G to G, LG, and this take an element of the group U, and so gives an element LG of U. And this is defined as the multiplication in left side for U. And so I have G, so in the left side here, for U. There exists another map that is RG, and this is the right side. And so I have RG to G, from G to G, and I have an element U, and this is RG of U, and is defined as U for G, so in the right side. Okay, perfect. So in the right side, G. We are interested in this transformation, in the left transformation. This transformation is called left translation. Okay, why left translation? Because attention, here I have this operation that it isn't a multiplication, and this isn't a sum. It's a general operation. I don't know which kind of operation, okay, but I have that if, for example, is a multiplication, I have if I assume, for example, I have U plus G, and so if U is here, I can sum with G, and so this is U plus G, and so this is the left translation. But when I start talking about commutative operation, for example, the sum in R, for example, R to N is an abelian Lie group. For example, in this case, I mean, it doesn't any sense to talk about or left translation or right translation, because for a commutative group, so for an abelian group, I have that G for U as equal to U for G. Okay, this in an abelian group, not forever group, just in abelian groups. Okay. So now this is the left translation, and I have that this map. Okay, I want to give a very important. I am interested in this left translation. Okay, in this lesson we are interested in this transformation, in this map. Okay, perfect. I remember you that you can share it. You can share this lesson to. You can share this lesson. It's very important for me, and I think this lesson can be very interesting. Okay. Now, of course, Algae is an isomorphism. Okay, Algae is an isomorphism. Now, this map Algae induces, induces another map, and so if I take the push forward of this map, okay, I obtain a particular, so Algae dual So this is the push forward of this map, and I take the push forward. I obtain this thing. For example, acting over vector x of gh, okay, is equal to Lg dual, the push forward, over xh. Perfect. Now, so this is a map acting over a vector x. Now, if I have that Lg dual acting over x is equal to x, I have that the vector x, is called a left invariant vector field. If x, of course, if x is a vector field, I have that in this case, the vector field is called a left invariant vector field. Okay, so you have some questions about this topic, or can I go home? Okay, so we don't have any question about this. Okay, so we can go home, I think. I think we can go home. Okay. Perfect. Okay, now, so we have? We have that. The set. Attention, a moment, please. So, definition. So we defined the left invariant vector field now, and now the definition, another definition, the set of all left invariant vector field. So the set of all invariant vector field x, okay, is called, okay, vector fields, of course, on a Lie group, because now I have that Lie group is a smooth manifold, okay, with a group structure, and so I have that is a smooth manifold, so I can have a tangent space, and here I can find a vector field x, okay. Now, the set of all invariant vector field on a Lie group is denoted as Lg. So the set of all invariant vector field is Lg, and this is the Lie algebra. So what is a Lie algebra? A Lie algebra is a set of vectors. So it's a vector space. And it's a vector space, and I have that these vectors are left invariant vector fields. Okay, and so I have that this is a subset of the set of all sections over the tangent bundle TG, where the tangent bundle TG is the union of all tangent spaces over G, and the set of all section is a map of this kind, mapped from G to TG, such that pi C is equal to identity of G, where pi from TG to G. Okay, perfect. And so the Lie algebra is endowed by a commutator. So In this case, I have a vector field x. So I have this Lie bracket. Okay, this is a Lie bracket, and so a differentiable Lie bracket. And this differentiable Lie bracket is a bit different is a bit different from the normal commutator of this kind. Okay, here these two are a bit different. Okay. Perfect. Okay, sorry, a moment, wait a moment, please. Perfect. So I have the Lie algebra is the subset of all sections over the tangent bundle, and this is a section. Okay, so this gamma set is the set of all sections over the tangent bundle. Okay. And so I have this differential Lie bracket. Which are the properties of this Lie bracket? Okay, go on and let's see these properties. I have so 1 x y. So for example, this differential Lie bracket as a is a map from the Lie algebra, from the Cartesian product between two Lie algebra and two Lie algebra, okay, of a Lie group. Then to x y is equal to minus y x, okay, and then we have the Jacobi property. The Jacobi property is that I have x y theta, okay, this is equal to this is equal to, or I can write in this way. Okay, I can write plus, so this commutator, this Lie bracket plus this y x theta, okay, plus plus zeta x y is equal to 0. So the sum of these three members is equal to 0. Okay, perfect. So these are the properties of the Lie algebra of a Lie group G. Perfect. And now for definition, we have that this is a subset of is a subset of the set of all sections, and I have that an example of Lie algebra is this, the set of all section over the tangent bundle. Perfect. Okay, this is an example of Lie algebra. And then a theory is that the set of all left invariant vector fields and taught by a Lie bracket, so this is a Lie algebra, is a subset, is a Lie subalgebra, so is a subalgebra, is a Lie subalgebra of this. Okay, Perfect. And now, an important theorem, a very important theorem is this. I have theorem, the Lie algebra is isomorphic to the tangent space to identity of the group. So, someone knows why this. So someone knows how to prove this theorem. So why the Lie algebra is isomorphic to the tangent space of the group at identity E. Why? Someone knows? Oh, okay. I think maybe we can, if you wanna, we can show this theorem, or how to prove this. So if I take a smooth manifold, so this is, and with a group structure, and I have a tangent space to at identity E. Okay, and this is isomorphic to LG. In fact, in many exercises, I have that. Many exercise, I have that. I have that to find the generators of the Lie algebra, and now we are going to see what's a generator of a Lie algebra. So to find the generators of a Lie algebra, I must find a base for the tangent space, okay, at identity of the group. Perfect. So this is an important result. This is an important theorem. Okay, so now I go on, and then if somebody knows how to prove this theorem, we can turn it. We can turn here. Okay. Now we can talk about an important. We can talk about an important part of the lesson: the classification of Lie algebra, of Lie algebras in general. Okay. Okay. So, consider a Lie algebra involved, of course, by a Lie bracket, and then we can take we can say that this is a vector space, of course. So we must remember that Lie algebra is a vector space, okay? And so I have that as a particle, of course, vector space with some particular properties, of course. And I have that this is a C space, okay? So it's a vectorial space, it's a vector space constructed over the field of the complex numbers. Okay, and now, so we have that G as a complex manifold. In this case, a complex manifold is a manifold whose transition functions are holomorph. Okay, perfect. Great Kepler. High automatore. Okay. Now, so theorem. I have that every finite dimensional complex Lie algebra. So every finite dimensional complex Lie algebras. So LG. Perfect. So every finite dimensional complex Lie algebra can decompose in a particular sum. Okay, I can so write L as equal to R direct sum R plus L1 direct sum, of course, Ln. Okay, perfect. So what is R and what are which L1, L2, L3, L4, and so on until Ln. Okay, I have that R is a particular Lie subalgebra of L, and so I have where R is a subalgebra. As a subalgebra of L. Okay, but of course, this subalgebra is a Lie subalgebra. This subalgebra, I think, you think, of course, it must have some particular property to be the subalgebra that must decompose the principal Lie algebra L. In fact, this subalgebra must have these particular properties. And which are these properties? So I have that is attention solvable. Solvable. What does it mean? What does solvable mean? So a Lie algebra, a subalgebra, in this case is a subalgebra, but a Lie algebra to be solvable must satisfy this property. I have that the set of all commutator between two vector R1, R2, okay, such that R1 and R2 are in R, are in R, okay, is defined. So this set is defined as the commutator between R and R, okay, and himself. And this is a subset. This is a subset of this commutator R1, R2. Sorry, RR, okay, RR. R. Okay, and this is a subset. This is a subset of attention of this with another. So I have R. This kind and another R. And so on. So this is a subset of this thing with another, with himself, the commutator between this and himself. Okay, and so on. Perfect. So this is the definition of a solvable Lie algebra. Okay. Perfect. Now, so this is the definition of the solvable subalgebra R, and the definition of L1, L2, L3 until Ln, which is the definition of this Lie algebra. Lie algebra, sorry. I have here, so in this case, I have so L1, L2 until Ln are called simple Lie algebras. So attention to this adjective because they are simple. Okay. When a Lie algebra can called simple. First, I have first point. Li is non-abelian. So Li is non-abelian. 2. Li contains no non-trivial. Attention to this proposition. Attention. No non-trivial ideals. What is an ideal? An ideal is a subset. I is a subset of the Lie algebra L such that the commutator IL is a subset of I. Okay, perfect. And we I think we've already met this ideal, this concept of ideal. I think in the third lesson about mathematical methods for quantum mechanics. In fact, we talked about the construction of tensorial algebra, symmetric algebra, and to construct these kinds of algebras, we need this concept of ideal. In fact, we have a quotient space between the tensor algebra and of course this ideal. Okay, and we have different cases. For example, cases with where the ideal is spanned by by a veg product. So we can talk about the veg algebra. This is the wedge product. Okay. So these are simple algebras, and so sorry, here I forgot the us. Okay, the us, and Li is non-abelian. Li contains non doesn't contain non-trivial ideal, so contains trivial idea. So this means that I, for example, there is a subset can be or L or the famous zero set. Okay, empty set. Okay, so non doesn't contain non-trivial. Okay, perfect. Now, I defined the solvable subalgebra, and I defined the simple Lie algebra, and so now I have that the Lie algebra, the principal Lie algebra, can be decomposed. So here, but now I've used before I've used two different kinds of direct sum. I have here as this kind, and here I have L and okay, Ln. What does it mean? What is this and what is this? I have that L1 Lie L2 as defined as the normal sum, direct sum. Okay, so I have this. Perfect. And I have that in this case the commutator between L1 and L2 as equal to 0. Okay. So this and why? Whereas for this kind of direct sum, I have I have what? I have R direct sum between a simple Lie algebra L1 as defined as R. So the direct sum, of course, the direct sum between R and L1, but in this case, I have that the commutator between L1 and L2 is equal to 0. And this another case, I have RL as, is a subset of R. Is a subset of R. Perfect. So this is the definition. This is a definition of this kind of direct sum. Now, if you have some question about these topics, you can talk now. Okay, you can talk now. So, if you have some questions, you can ask. I don't think so. I don't think so. Perfect. I remember you that you can subscribe to Telegram group and Discord channel, okay, and of course to this channel, YouTube channel, and you can find everything in the description of this video, and in the description I think of every else video, okay. Matteo, the theorem says that a finite-dimensional complex Lie algebra admits a solvable Lie subalgebra. In fact, I have that every finite-dimensional complex Lie algebra can be decomposed in a solvable subalgebra R and simple Lie algebras L1, L2, and until Ln. Yeah. This is the theorem, and now I can have particular cases where L is equal to just the decomposition between say simple algebras. So this. So what does it mean? This. Matteo said this thing, so that the theorem says this, okay, but in the way that you used to talk about this theorem isn't always right. Why? Because there are some cases where the Lie algebra can be decomposed in just sub-algebra, simple Lie algebras. So the theorem says that I can decompose the Lie algebra in this sub-algebras, but there are cases where I can just decompose the Lie algebra in simple Lie algebras. In this case, I can talk about semi-simple Lie algebra. So an algebra that can be decomposed just in simple Lie algebras, is called semi-simple Lie algebra. Semi-simple Lie algebra. Davide, I can't. Sorry, I can't. But this video is a video for an English course about quantum field theory. So this is a lesson about some mathematical method that we can meet in the study of quantum field theory. And I thought about this course as an English course. And so it's open to everyone, Italian people, English people, and so on. Okay. So this is the definition of a semi-simple Lie algebra. Okay. Perfect. So this is the first remark that I can do. So this is a remark. Okay, a definition of an expansion. Thanks for the lesson. Thanks to you that you watch this video, and I'm very happy that you like it. Okay. Okay. Now. Now. We can. Okay, perfect. We can define a particular map. Okay, a particular map. Okay, so definition. So now we're starting. We start talking about classification of Lie algebras. Okay, so we are going to talk about this of the Lie theory, the classification of Lie algebras, and so we are going to talk about Dinkin diagrams too. Okay. Perfect. Now, so definition. I take a Lie algebra L with commutator with Lie bracket. Okay. And I say that this is a complex Lie algebra. Okay, is a complex Lie algebra, and I have H. H is a vector in the Lie algebra. Okay, and I have the adjoint map. The adjoint map is a linear map from L to L, so it's linear. And so I have, if I take a number L, the map gives me a number and H for L. And this is defined as the commutator between H and L. Okay, so we can say that a joint map is equal to this. So this is the vector that I must add, okay, to the expression. In this case, I take an arbitrary vector L. Okay, so this is the adjoint map. This is a definition that we can use in the future. Okay, that we probably use in the future. Now we can define a very important thing. Okay, so in differential geometry, to understand this lesson, you must know what is differential manifold, a smooth manifold, transition functions, tangent space, cotangent space, tangent boundle, phi boundle. I don't think so, but before we've met the tangent boundle, but the tangent boundle is a particular type of phi boundle. It's a union of tangent spaces. But the very important definition that you've already met to understand this video is what's a smooth manifold, what's a vector field, and what's a one form. For example, a one form or an form. Okay, perfect. In fact, now we are going to talk about. We are going to talk about the killing form. Okay. before okay, I can read a comment. Alessandro, how do you learn English and its pronunciation, and how much? Oh, sorry, the scam is off. Okay, how do you learn English and its pronunciation, and how much time do you need to reach this level? So, no, I don't like. I hate. I hate memory trick. I hate every type of memory trick, and s- of course, school helps me to learn quickly English. But I think the most important thing, the most useful thing to learn English is watching and listening TV series in English with subtitles in English. For example, I can say that I learned English watching Marvel films, for example. So, forever you study in your famous style study. I mean, do you repeat? Now in this last period, I start studying just books in English. But before to start studying this kind of books, I just study in Italian. Okay, but now I study from lectures in English, for example, the lectures of the professor Frederick Schuller, or the lectures notes of David Tong, David Skinner, and so in this last period I start studying just in English. I think it's another way to learn quickly English. I think, and then so listening, watching, and studying and talking, speaking, okay, in English. These are the most important ways to learn English, to learn quickly English. Okay, so go home and we can talk about the killing form. Okay, killing form definition. So another definition. I remember you that tomorrow we are going to talk about mathematical methods for quantum mechanics, and we are going to talk about Hilbert space and Fourier theory in functional analysis. But the lesson tomorrow, the lesson will be, I think, in Italian tomorrow. Okay, so now what's the killing form? So the killing form definition, we have a particular map, the bilinear, okay, the bilinear map key from L for L, okay, to C, and I have this particular thing, key AB, as equal to the trace of a joint A, C composed joint B. Perfect. And this is the killing form. So key of AB is equal to the trace. Okay, so for this reason, I have a scalar, okay, here, because trace is the sum of every diagonal element of my matrix. In this case, the matrix is the composition between the adjoint map of A and the adjoint map of B. So this is the killing form, and it's very useful together with Cartan subalgebra, for example. It's a particular kind of subalgebra. Okay. Now, I have that if L is a finite dimensional vector space, I have that K as AB as equal to KBA. Okay, this is the case. This happens when the Lie algebra is a finite dimensional vector space. Okay. Perfect. And if L is semi-simple, I have that key is degenerate. Okay. Perfect. Now I have this particular thing. Okay, attention please, because now I have now we want to consider the components of this map. Okay, because this map has a matrix. This map. Okay. As a matrix, and so and the components of this map and of key. Okay, perfect. And so we want to calculate the components of these two matrices. Okay, but with respect to what? Right, with respect to some arbitrary basis, maybe. And so I choose a basis E1, E2 until E dimension of L, of course. Okay, so I don't know what's the dimension of L, and so I index this with a dimension of L. So this is a dimension of L, and then epsilon. This is a map of L dual, so the dual vector space. Antonio, how old are you? I'm 13. I'm 13, and so I choose these two bases for to calculate the components of the adjoint map and the killing form. Okay. And now I have the adjoint map of EE J key. Why? Here I have these two. I have these two. These two things. Okay, these two indexes. Why? Because the definition, of course, of the adjoint map as this, as like this. Okay. So this is an arbitrary element that I can choose. And so I think the question of Francesco, if you are good in English, and if you don't have any problem in English, you can start studying English. If you prefer studying in Italian, we can start. Attention, because you can just start studying in Italian, because when the level when the level will become more difficult, you must study in English. Okay, but you can, if you prefer, you can start in Italian, and then you continue to study in English. Okay, so I have the adjoint map with these two indexes, and this is equal to so this is the definition. Perfect. And now this is equal to this. Okay, perfect. Now, attention, because I have a particular thing. I have that. So I chosen these two bases for my vector space L. But I have that I can express my that I can write. Sorry, I can write the components of the adjoint map. Adjoint map, and this way. Okay, and here I have this commutator. Now we can start talking about generators of my Lie algebra. In fact, I have the E key, okay. In this case, I have this commutator, and I have that this is equal to a particular product between two elements. These two elements are the structural constants. The structural constants is this Cm Ik Em. So the commutator, because these two elements, what are these? This is a basis for my okay, for my vector space, and I and key can be equal to 1, 2, until the dimension of L. And so I have, for example, E1, E2, and this is Cm 1, 2, Em, and this can be something important. And I have here another element, so I can have E2, E3. I can have E1, E dimension of L, and so on. Okay, and so this is the structural constants. Okay, the structural constants, and these two elements are also the elements of a basis of the vector space, and this means that these are the generators of my Lie algebra, and every generator of my Lie algebra must satisfy this property. So I have the commutator between two elements of the basis of my Lie algebra, and this is equal to the structural constants for another element with an index m, okay, an arbitrary index m. Perfect. And so this is this thing that I can write now. Sorry, I can write this as, okay, this is equal to, so J for C I key E perfect. And so this is equal to CMI key for this. Attention now, because I have this thing. I have that I have a multiplication between two elements of a basis and a dual basis, and we know that the dual basis must be orthonormal to the principal basis, and so I have two elements, E alpha and E beta. I have that is equal to delta alpha beta. And so in this case, I have delta between these two indexes, and so I have C psi. Okay, so this is the this is what is the components. So it's structural constants. So the components of the adjoint map. Okay, perfect. the calculation of the components of the adjoint map allows me to introduce the structure constants of a Lie algebra. So when in the future we will meet a particular commutator between two vectors, for example, the most important case in physics as the SO3 group, as a spatial orthogonal group, a three-dimensional group, I have the commutator between the generator, that is the angular momentum, and here I have the Christoffel symbol EJK. JK, okay, this is an important case, and when happens this thing, I can talk about Lie algebra. I can talk about Lie algebra, and of course, I must see that is this Lie bracket satisfies the property of the satisfies the Jacobi property, and I have to the J as equal to minus JJ JI. Okay. Yeah, this is this is very important property of the Lie bracket, and then I have the Jacobi property too. Okay. Now this is the way to calculate the components of the adjoint map, and now we can calculate the components of a killing form key of a killing form K. Sorry, and how to calculate the components of the killing form. Of the killing form, I have to calculate these. We can take the killing form of two elements of the basis, and so I have EI, EJ. Okay, and this is of course the trace of a composition map. So this is the trace of this composition of maps, and I have that is equal to, of course, because I just calculated the components of the adjoint map, and so in this case I have the multiplication between two structure constants, CLIM for CM JK. In fact, then I have that. I have that. Sorry, a moment, please, because I have here is equal to KIJ here, and then okay. Okay. So now I have that. I can write this as the composition EI joint. Joint EJ L key, and this is I have key IJ is equal to CN IM for CJNM. Okay, so the components of a killing form is a multiplication between two structure constants. Okay, perfect. So this is the components of a killing form. Perfect. Then I have the definition of a Cartan subalgebra H. What is a Cartan subalgebra H? I must take a Lie algebra L. Okay, a Lie algebra L. And H, of course, is a vector subspace. Okay, this H is a vector subspace, and it's the maximal subalgebra of L, such that there exists a basis H1 until Hm of H that can be extended to a particular basis. And now I write it. Okay. If there is any question about this topic, you can ask. Okay. If you haven't any questions, I can go on. And so go ahead. Okay. And I can define the Cartan subalgebra. The Cartan with a French pronunciation. Because I think Cartan was a French mathematical. So Luca, I don't think so. I've just finished now a teaching about this. So now, so what's a Cartan subalgebra? And so yeah, okay. Definition. So H is a Cartan subalgebra of L. Okay. Cartan subalgebra of L. What's a Cartan subalgebra? So as one, okay, is a vector space as a vector subspace. Okay, subspace of L. Then over this space I can define a particular basis. So this is a maximal subalgebra of L. Okay, so it's the maximal subalgebra of L such that there exists basis H1 until Hm, where of course M, I have this relation because M is the dimension of this subalgebra, and N is the dimension of the algebra, and I have the so of H, of course. Okay, and this that can be expanded to another basis, to a basis of this kind, H1 until Hm. Okay, and now I have E1 and Ej minus M. Okay, perfect. And now repeat, it's the maximal subalgebra of L such that there exists a basis of this kind of H that can be expanded to a basis of this kind such that so what's the property of this basis? I have that for any adjoint map H, where H as in Cartan subalgebra, I have that adjoint map H over E alpha, okay, is equal to lambda alpha of H, attention, E alpha, with alpha is equal to 1 until t minus m, and so this is definition, attention, and so where lambda as an arbitrary function of H, and so I have this thing. So if I have this thing, I can talk about, I can start talking about Cartan subalgebra. So I have this definition of it. And the important result is a theorem, and it's that any finite dimensional Lie algebra possesses a Cartan subalgebra. And if L is simple, so if L, attention, is simple, I have that H, so the commutator is equal to 0. Perfect. Now, here I have lambda alpha of H. This is an arbitrary function of H, and I have that lambda 1, and lambda d minus m, okay, are called roots. What does it mean? Are called roots. And it's important, the root set phi, the set of all roots, lambda 1 until lambda t minus m. Okay, root set. So if every finite dimensional Lie algebra possesses a Cartan subalgebra, okay, and so possesses a Cartan subalgebra, and in definition of Cartan subalgebra, I meet the definition of these roots. So these roots are this element that satisfies this property, this relation with adjoint map, and it's very important in physics and the theory and mathematics. The root set, so the set. As the root set of all roots. Okay, so as the set of all the roots. Perfect. Okay, perfect. So I think that you say that you are a mathematician. You are a mathematic. I think you're a person that you studied mathematics to say this, because as very you must have very many experience to say this. So okay, so this is a root, okay, and I have the root set. Perfect. Now, now we can talk about a set of all fundamental roots. So this lambda are roots, okay, and I can talk about fundamental roots. What is a fundamental root? Okay, so I have where I can write. I have, okay, definition, I take the subset pi of the set of all roots. Okay, hi Loris, hi Gabriel, and so I have a set of fundamental roots pi. This is a subset of the set of all fundamental roots, and I have that pi as linearly independent. And so it's a family, it's a set of this fundamental root pi 1 until pi f. Okay, perfect. Then second point, for all lambda in phi, okay, for all lambda that lives within phi, there exists this family of number L1 until and f that live within n, such that there exists a number epsilon in this interval, in this set, sorry, plus 1 minus 1. And this, so this number can be or plus 1 or minus 1. And I have the lambda as equal to epsilon for sum over I of ni pi I. Okay, so this is, I think this is a definition of fundamental root. In fact, I have a root that lives within this family of root phi, and I have these f numbers n and 1 until n f, and these are natural numbers, such that there exists another number can be or plus 1 or minus 1, such that I can write lambda, so the root, out the fundamental root in this way: epsilon plus the sum over I of ni for pi I. Perfect. And an important thing is that theorem span over C of the pi as the dual Katana subalgebra. The dual Katana subalgebra. And a remark, I think a remark is that the set of fundamental roots isn't unique. So the function that associates a root with a fundamental root is not unique. Perfect. Now, we can talk about. I can give you some definition. Okay, some definition. Yes. I think today we can talk about representation theory. So in the next lesson we are going to talk about representation theory. Okay, so another definition. I have definition for any lambda in phi, okay, lambda in phi, we can define what this function s lambda from h dual over r linearly. It's a linear map, this, to h over r. Okay. And I have the definition of this map. So it's a linear map, and S lambda of a number mu of the dual Catan subalgebra over R. And I have that the dual Catan subalgebra over R is the span over R of pi. Okay, so the set of fundamental roots. Perfect. And so S lambda mu is defined as mu minus 2. So mu minus 2, this is a definition. of function. And I have key lambda mu k dual lambda. So this is the definition of the of this function. Okay, it's a linear function, but I have that to define this function I need to the dual killing form. So what's the dual killing form? If the dual Cartan subalgebra constructed by over R, here I have the killing form, the dual killing form has the dual killing form is equal to, so key as a map that is a map from H dual over R for H dual over R to R. Okay, and I have that key alpha as always major or equal to 0, and key dual of alpha is equal to 0 if alpha is equal to 0. Okay, Loris, yeah, it's right. Yeah, it's right. And then I love speaking English, so it's perfect. This kind of live streaming. Okay. Thanks. And so now, so this is the definition of the dual killing form, and using this definition, I can define this function. Perfect. Now we can talk about this S lambda. Okay, S lambda here. Why I talked about this? Why? Because S lambda is a particular and important, I think, transformation. In fact, S lambda is called Weyl transformation. S lambda is a Weyl transformation. This is the name of the function, and I have the set of all S lambda, so the set of all roots S lambda with lambda that lies within the family of all roots is the attention as the Weyl group. So the Weyl group is an example of group, and is the example and is the group of all S lambda with lambda that lies within the family of all roots phi. Perfect. Okay, so this is the definition of Weyl group. If you wanna see in more details the Weyl group, you can search on internet, on Google, because the Weyl group is a very important group. And in this lesson, I just wanna introduce it. But we'll see it again. Okay, see you soon. See you soon again. So Weyl group, perfect. Isaac, good evening. Thanks for the term, Mr. Dimaggio. What do you like? It's a good question, I think. when I was a young when I was a kid, when I was young, I loved speaking. I loved teaching to my parents, and when I am 13, and so I decided to open a channel because I love teaching. I love teaching mathematics and physics, and um, it's my biggest passion. Okay, and so damn, mathematics is so sexy, so cool, and so it's it's very cool teaching it too. Okay, and perfect. Now for my for my for my parents, my lessons are very boring. Okay, and so I decided for this reason to open this channel. I hope that for you these lessons aren't boring. Okay. Now, so this is the way group. So I hope that you aren't bored in this moment. That you aren't bored. Okay. Now, a particular a particular theorem is this. A particular theorem. Okay. So I have this theorem. Theorem. A theorem. I have first point. The Lie group. Okay, so Lie group G as generated by the fundamental is generated by the fundamental roots. The fundamental roots. Sorry for my writing. Good evening, Vincenzo. So roots. So G is generated by the fundamental roots. Fundamental roots pi. Okay. Perfect. Two. So this is the first point. The second point. Is that every root. Okay. Every root. Lambda. Okay, can be produced from a fundamental okay, fundamental pi. By action of the weight group. Okay, so this is another important point. ITGCOM. Hi. So an important point is that every root lambda can be produced from a fundamental root pi, okay, by an action of the weight group. This, okay. Perfect. Now, consider this thing. So this is an important theorem. There's two important theorems, actually. And I have that I can consider the set of all epsilon for the sum over I of ni for pi I, and this is the set, okay, the set of all roots. The set of all roots. Okay. Of course, thanks for watching. You are I thanks. Okay, and so I have an element of this of this set of roots. Okay, and s okay, a pi I pi j. Attention, this is a definition, okay, as a definition of what is this. Because I have the fundamental, the wave transformation as lambda. In this case, if I take a fundamental root, what happens? What can happen? And here I have pi j. And so I have pi j, okay, plus 2 minus, minus 2, I have here pi j for minus 2. So this is a definition, attention, okay, as a definition, key pi I pi j over key I pi j for pi I. Okay, so what did I do? I take the wave transformation as lambda. Okay, I take this, and then sorry. Okay, I take the. So here I have plus, okay, isn't a multiplication, as of sum pi j plus minus 2, so pi j minus 2, but why I put in this this bracket? Because I have that this number here as a natural number. Okay, in fact, I have these two killing form that can be negative, and then I have multiplication with a negative number. So here, this quotient is a negative number, and so I have that this negative number for a negative number is a positive number, so a natural number. Perfect. Now we can define the Cartan matrix. So the Cartan subalgebra is equal to 2 for the dual killing form. Sorry, the Cartan matrix pi I pi j or key pi I. Perfect. So this is the definition of the Cartan subalgebra. Perfect. Now we can define a particular matrix. This matrix is called Nij. Okay, Nij is obtained by Nij is obtained by Cij Cji. Perfect. And now this is equal to if I take Cij, okay, so Cij is equal to this. Then I can take Cji. So here I have pi j pi I, and here I have pi j, and so I obtain this 4, and of course I have 2, so 2 for 2 as equal to 4. 2 for 2. Perfect. So, okay, sorry, a moment, wait a moment, please. Okay. And now, so Cij for CGI for the killing form, okay, key of pi j over killing form pi I, and here I have the killing form pi j, and sorry, pi j pi I, and here I have pi j. Perfect. Okay. And this is what? So this multiplication can be expressed in another way, and this other way is I can talk about the cosine square of this. This is equal to the cosine square. Okay, the cosine square, of course, 4. So this is the cosine square for of the angle. So this is an angle here from pi I and pi j. So the cos for cosine square of the angle between pi I and pi j. Perfect. And so now I can write a map Cij, Cji, and here I have Nij. Okay, and so I have, for example, 0, 0. Of course, I have here 0, for example. Then, so because it's a multiplication. Then I have -1, and here is 1, for example. And then I can have -1, -2, or maybe -2, -1, and this is of course 2. So I have this set, okay, and so on. I can have, for example, -1, -3, -3, -1, and so I have 3 here, and so on. So Nij as positive. Perfect. Now, to finish this video, we can talk about Jinking Diagram. So this is the definition of Catan matrix. This is the definition of this matrix Nij, and so this is the values that the matrix can have. For example, 0, 1, 2, 3, and so on. Of course, they depend on the values that assume the Catan matrix. Okay, yeah, I'm talking about Lie groups. Now I'm going to talk about Dinkin diagrams. So the Dinkin diagrams is the nucleus of this teaching. Why? Because I introduced the topic using the concept of the classification of Lie algebras. Okay, and so now we can talk about the Dinkin diagrams. In fact, I have what? What is a Dinkin diagram? Okay, a Dinkin diagram. A Dinkin diagram is a diagram. So it's a draw. It's a particular draw, and this is the rules to draw a Dinkin diagram. The first rule is that every fundamental roots, every fundamental roots pi I. So for every first point, for every fundamental roots, okay, draw a circle. So a circle is a fundamental root. Drawing a fundamental root is a circle, okay? So representing the fundamental root, a fundamental root with a circle. This for every fundamental roots. Okay. Second point is that if I have two circles, pi I, pi j, okay, so these two circles represent pi I and pi j, and pi, the set of all fundamental roots. So I have these two fundamental roots. I must draw, attention, I must draw Nij. Attention, I must draw Nij lines between them. What does it mean? So, for example, I can have 0 lines. I can have 0 lines. I can have 1 lines. I can have 2 lines, and so on. But I have here Nij, and so what's Nij? I just defined this before. So I have that Nij. For example, I have 2 Catan matrices, and so I have the multiplication between these 2 Catan matrices, and are based on these 2 fundamental roots. And so, if, for example, I have Nij is equal to 0, I have 0 line. For Nij is equal to 1 line, 2 lines, 3 lines, and so on. Okay. Perfect. Now, if there are 2 or 3 lines between 2 circles, so, and 2 circles, we have seen this symbol, okay, here. So, for example, if I take this, okay, what does it mean? This circle, okay, draw here maybe, okay, so, okay, so I have, for example, two circles and 2 lines, pi I, pi j, and if pi j is minor of pi I put this symbol, okay, perfect, just this, perfect. So if this pi j is longer than this pi I, these straws are called Dinkin diagrams. Okay, so a Dinkin diagram is a particular way to represent a Lie algebra. In fact, now I have this particular theorem. So this is the 3 principal rules to draw a Dinkin diagram. Okay, perfect. Now we can. I can show you this theorem. So theorem, and this theorem helps us to understand where we need of these Dinkin diagrams. So these particular draws. Okay. Any finite dimensional C Lie algebra. Okay, so constructed over the C field can be reconstructed from its set. Can be reconstructed. Okay, from its set pi. I remember you that where do fundamental rules born? When we talked about the Catan subalgebra, we defined the root, and by roots we defined the fundamental roots. So now an infinite dimensional Lie algebra can be reconstructed from its set of all fundamental roots pi, and I have this thing. I have the, sorry. Okay. Perfect. For example, AL, this Lie algebra. AL is, I have A1, then I have A2, okay, and then I have A3, and so on. This is AL for L. Okay, I have this L, and so this is the first example. Then I have example BL, and BL what is? I have L. In this case, I have this, and so there isn't any cases here. Here I can write, for example, A, okay, A4, so and so on. There isn't any case, okay, because L must be equal to 2 or minor to 2. And so I have that first case is the second case for AL, and I have here, here I have I have this. Okay, in the first case, and this is B2. And then I have this case, B3. Then I have the B4, and B4 is B4 is I think is as this. Okay, and so on. Perfect. Then I have CL for L minor 3 in this case, and so there isn't any case for L is equal to 1, there isn't any case for L is equal to 2, but there is a case for L is equal to 3. In fact, I have this. Okay, I have this, so this is C1, and then I have this. I have C2, and so on. Okay, and then I have DL. DL for L. There isn't any case for 1, for 2, for 3. For 4, I have, okay, for 4, I have this thing. Okay, this is D1. Perfect. And then I can have, in this way, D2. I can construct D2. I can construct D3, and so on. And then I can construct some other set, for example, EL, and so on. Okay, so what is A1, A2, A3, A4, B2, B3, B4, C1, C2, D3, and so on? These sets are Lie algebras, and I just represented this set, this Lie algebras, like using a diagram called the Dinkin diagram. Goodbye.